Thanks, Webb, for the invitation and for organizing this really interesting workshop. It's a pleasure to be here. In my lab, we work on a variety of image reconstruction and different problems in computational imaging science. Today, I'm going to be talking about some specific results pertaining to photoacoustic computed tomography, which is one of the longstanding projects in my lab. And what I'm going to be showing, I think, are examples of win cases for deep learning applied to large-scale, even three-dimensional problems in medical imaging that can be applied robustly in practice. Right, so beyond MRI, we know that there's not a lot of work where deep learning methods have really made it to the clinic, and certainly have not been applied to three-dimensional problems. So hopefully I can get you a little bit excited, maybe envious about our use cases here. Okay, so I'm going to start off just with a lightning quick description of what is photoacoustic tomography, because I suspect some of you may not be familiar with it. And then I'll talk about these use cases, which I think are atypical. So let's think about the standard use cases for deep learning and image reconstruction. One, the obvious thing, learning a data-driven prior, like we've heard about before. You have an ill-posed problem, you're brave, you want to solve it. That's fine. Maybe you want to use deep learning to speed up your reconstruction. Maybe you have in your workflow, you have a need for a very fast reconstruction. Maybe you want to live the Bayesian dream. You want to sample from posteriors, right? Do things that we just couldn't do before. But these are wonderful, wonderful use cases for deep learning in reconstruction. Today we'll be talking about something different. The first use case has to do with basically using deep learning to approximate an inverse mapping that we know exists, we know it's stable, but we can't put our hands on it. We don't have an analytic description of it. So I'll show two examples of these that are both very relevant to photoacoustic computed tomography. And then if I have time, I'll talk about how we also compensate for the spatial impulse response of transducers in photoacoustic tomography. And again, the general theme in this talk is that we're using more or less standard supervised learning methods, but applying them to specific problems in a way that they work well, they generalize in a fantastic way, and generally can be useful. Okay. So this is my one slide on photoacoustic computed tomography. This is a coupled physics modality that involves optics and acoustics. The basic idea is as follows. Consider that you have an object here, which is this gray textured region. You basically have a laser, you send in a pulse of light, you irradiate this tissue. The light travels inside the tissue, it gets absorbed quickly, and that optical energy is converted into acoustic waves within the tissue. So you send in a pulse of light, the light gets transferred into acoustic sources inside of the object, and then the sound waves travel outside of the object in the normal way. These blue squares represent an ultrasound array, which surrounds your object. At each transducer element, you basically measure the pressure signal that arrives there. So at each of these transducer locations, you're measuring a time trace, which is the measured pressure as a function of time. That's your so-called projection data here. And then once we record this data, then we do image reconstruction. Essentially, we use an algorithm to produce an estimate of the initial pressure distribution. You can do other things. This is the vanilla version of photoacoustic tomography. But again, we're basically assuming a linear model where P is our measurement data, H is our forward operator based on the acoustic wave equation, and P naught is our sought-after object function. Okay, so let me talk about this first application where we want to approximate existing but unknown mappings. But first, let me just remind you all about some of the concerning behavior that we have when we use deep learning to solve ill-posed problems, which is again probably the most common use case. And we all know that robustness is a concern. Hallucinations and instabilities can exist, and if they exist, they might not actually be rare events. This bad behavior is generally associated with the null space of a forward operator. And I have a wonderful citation by Gottschling and colleagues on the troublesome kernel at the bottom here. But in general, when you have an ill-posed problem, has a null space, and you do an end-to-end reconstruction, inevitably you can observe this sort of bad behavior. You can get around it if your algorithm is somehow null space aware, right? If you incorporate enough physics into your method, but it's something we need to be aware of. Okay, so here's my problem statement. Again, consider that we're given knowledge that a stable linear inverse mapping exists, but it's not analytically available in closed form. Okay? Of course, we can use iterative methods to try to find a solution, and that's what in my lab we've been doing for the past 20 years, developing iterative methods for this type of modality. That's great. But for large 3D problems, of course, this may be slow. It'd be nice if we had a fast one-step procedure. And that's what we're going to be talking about. And the use cases where we actually have the scenario correspond to a situation where we measure half-time data and half-scan data. These are both different forms of incomplete data that are intentionally measured in photoacoustic computed tomography. Okay, so again, here's basically the plan. We know that we have a well-posed mapping. I'm going to tell you why we have that in a moment. In this case, we expect the learned approximation of this mapping to generalize very well, especially if we incorporate a little bit of physics into the problem. And the approach we'll take is to use a learned filtered back projection approach, which I state here in its generic form. So again, our FBP method is just formed by taking the adjoint of our forward operator, which is also known as the back projection operator, and then acting it on a filtered version of our measurement, which in this case is the pressure data. In our problem, of course, we don't know what the explicit form of this filtering operator is, and that's what we seek to learn here. So if we can somehow learn an approximation of this filtering operator, we'll have our FBP method for these different types of incomplete data. Okay, so let me talk about the half-time data first. In its canonical form, and let me consider 2D for now, the forward operator in PACT is closely related to a circular radon transform. Right? So if you consider the schematic here, we have our object, we have our transducer array. If I take a particular transducer in the array, then the measurement data essentially is related to integrations over a family of concentric arcs that are centered at that transducer location through our object function. So this is a classic circular radon transform. Okay? And typically when we have complete data, we assume that at each transducer location, we're measuring all of the integrations over these arcs that intersect the object. That's our complete data, or I might call that full-time data. Okay? Half-time data are obtained when we only measure the arcs that go to the center of the object. So again, here's our circular radon transform, where we measure all of the circular arcs for our radius or our time between 0 and 2r. Capital R is the radius of our scanning system. In the half-time data, we only measure half of them. So we're only measuring half of the arcs here. For those of you who are familiar with the radon transform in CT, just consider the radon transform, 2D radon transform. Consider a particular tomographic view, but you only measure the line integrals through half the object, right? That's analogous to this. Of course, in the radon transform case, we know that if you take 2 pi worth of measurements, well, you still get all the line integrals. So it could be, because of the beautiful evenness symmetry of the radon transform, you only need that. It turns out the exact same thing is true here, but the symmetries are not nearly as transparent. Okay. And that's what I want to remind you about here. So it has been shown that half-time data are sufficient for unique and stable recovery, just like in the radon transform case. And this was established in the math community, basically in a continuous setting through the results of functional analysis and microlocal analysis. Right? So we know that at least in the continuous case, wow, we should be able to reconstruct an accurate image stably from these type of data. Like I mentioned, there's no analytic inverse mapping, so there's no FBP type formula that has been derived. Even in the math community, they've tried very hard. Iterative methods, I already told you, have been deployed, but we're going to get around this to learn a stable and quick filter back projection algorithm. Okay, so let me give you some details about the study we did. So this was a 2D study. We considered a discretized half-time circular radon transform operator. We considered 512 transducers on the ring, or 512 tomographic views, a 256 by 256 grid, a 2D CNN, which is very similar to a UNet, was employed to learn this unknown filtering operator. And we compared it to a reference method, which was the FBP method applied to full-time data. And then we also implemented a standard image-to-image UNet, just as a comparison, where we reconstruct an image using a back projection operator and then use a UNet to map that to a restored image. Okay, again, this is a simple schematic of the workflow. We have our half-time data, again, our temporally truncated data. We filter it using a learned filter operator and then just apply our known back projection algorithm. And again, a nice thing here is that the back projection algorithm's involved, so it is constraining the problem. There's some physics involved here, right? Because the range of the back projection operator is the measurable subspace of the domain of H. The loss was a standard reconstruction loss, nothing fancy there. Okay, so let me show you that my claims make sense. Here's a description of the data sets. I'm going to show you first some synthetic data sets. In the next study, I'll show you the experimental data. We considered 3 ensembles. One was these 2D slices through numerical breast phantoms, which were developed in my lab and basically derived from the FDA Victory project. The second set was a collection of clinical lung CT images. And then the third set were basically images that were stochastically produced from a mouse atlas. Okay. This is just showing an embedding, a T, S, and E embedding of these three data sets, just to remind you that the statistical properties of these images were quite different. So what we did was we trained our model using one of these data sets and tested on the other. So this is like an extreme test of generalization. And here are some results. On the left, we have the results corresponding to the use of the numerical breast phantoms. And again, the numerical breast phantoms in this particular case were used to train the model. So these are the in-distribution results. The first column is showing our reference image, which is basically the full data or the full-time FBP. So this is more or less the ground truth. The middle column is showing the results of the learned half-time method. Key point is they're very similar. And the third point is the results from the image-to-image unit, which also worked well in this in-distribution case. The middle row shows the error maps, and then zoomed-in sets are shown in the bottom row. So in distribution, this shows that the learned method, yeah, it worked very well. It's very close to the analytic full-time result. Again, the middle and the right are showing the results when we go out of distribution using the lung CT and the mouse data. And again, the good news is the same thing happens. The learned half-time method produces images that were virtually identical to the ground truth images. In this case, the image-to-image unit, it didn't do poorly, but you could tell it started to degrade. We wouldn't expect it to do as well because it wasn't constrained by physics. It didn't involve that back projection operator. And the same thing for the mouse data. Again, even though the model was trained on the breast data, the FBP method worked perfectly fine. Right? So this is kind of corroborating my claim that yes, we're trying to learn a well-posed mapping. There's none of this weird business that's going to go on. The model will generalize wonderfully. Let me go to the second use case here, and this has to do with half-scan data. So now we're moving to 3D, okay? And this is kind of a very, very practical use case because a lot of the instrumentation builders nowadays have moved away from 2D ring array systems to full 3D systems, okay? And so I've had in the inset here, this is showing an example of a breast exam. Breast imaging is one of the application use cases that's being actively pursued. So typically a patient will lay on a table with the breast immersed in an imaging bath, and then there'll be a transducer array and they'll acquire data. Okay, so there's two types of data. First is the full scan data, which is not compatible with the experiment. In the full scan data, basically you acquire data on a sphere, right? Imagine you have a sphere and on the sphere you have transducer locations, and at each transducer location you measure a pressure time trace. Clearly not compatible with our clinical application. More compatible with our clinical application is this half scan data where we're only measuring data on a hemisphere. Okay? So for example, in practice, they'll often have an arc array of transducers and they'll rotate this around in the process, basically acquiring samples on a hemisphere. Okay? Well, that's fine, that's great, but we know that full scan data is sufficient for reconstruction. There's FBP algorithms available for full scan data, but they're not available for half scan data. But the good news is that like the half-time data, the half-scan data are also sufficient for unique and stable recovery, right? Again, mathematically, you can show that. My group has some papers on this. But again, there's no closed-form reconstruction methods available, okay? And we don't want to do iterative reconstruction because I'm going to show you in a little while it takes a very long time because the data dimensionality is very high here. These are just some examples of images reconstructed using a standard FBP method that assumed complete data on the sphere. On the right, you can see, okay, yes, very, very accurate. On the left, this is what happens when you apply a standard FBP algorithm to half-scan data. You get obvious artifacts here. So we want to get away from those. So in terms of the methodology, it's very similar to what I just showed you regarding the half-time data. Again, we have a linear forward operator, and we're going to stipulate a FBP algorithm, and our goal is to learn this unknown filtering operator in a data-driven way. Okay. And again, we're going to use a supervised learning approach, and we'll use a CNN type of network, but now it's going to be a 3D network. And again, this network is linear. I probably should have mentioned in the half-time case, it was also a linear network that was used. But again, we have our object, we have data acquisition, our half-scan data. We learn how to filter it, and then once we learn how to filter it the correct way, we can back project it, we can get an accurate reconstruction. Okay, and I should mention this work was done by Pan Chen. in collaboration with members of my lab. And the halftime work was actually done by Rafik Mert-Kam. Okay, let me describe the data sets for this study. I'm going to start off showing you some synthetic data sets. Sung-Young Park in my lab has actually developed a very wonderful stochastic breast phantom, again, derived from the Victory project from the FDA, where we can create large numbers of breast phantoms that are relevant to PACT imaging. So we created 5,000 of these data sets, and we also conducted some out-of-distribution tests that involve experimental data. Okay, so let's start off with the in-distribution tests using these synthetic 3D breast phantoms. On the left, this is our reference image. This is using a standard FBP method, assuming that we have full scan data. We have data on the sphere. Again, it's not a realistic scenario, but we're doing virtual imaging here, so I can do what I want. It's our reference. In the middle, we have our learned FBP method now applied to half scan data. It looks very similar to the reference image. And on the right, we have the result of using a standard FBP method, but applying it to the half scan data. And you can see there's some obvious artifacts here. And the profiles confirm the same story that I just told you. So it seems like everything's working very well, at least in this in-distribution case. Now let's go to out-of-distribution, but still use synthetic data. In the top row, I show the results where we used noisy data with a different type of breast, a breast with a different density than was used in the training process. And in the bottom, we show actually this is a mouse phantom, the Moby mouse phantom, completely different. But again, the story is the same. Our reference images on the left, the learned half scan FBP method in the middle, and then the standard FBP method applied to half scan data on the right. And again, the learned half scan data just looks very close to the reference image. So again, very, very consistent with our expectations and very exciting actually. So now this is probably where it's even more exciting. We apply this to experimental data. And the data were provided by Alexander Orieski, our collaborator from TomoWave Labs. And again, we used our proposed learned half scan FBP method. We also applied the standard FBP method to half scan data. And now our reference method was obtained using a PLS TV estimator, kind of a standard iterative method using TV regularization. It's not an ideal reference image, but that's kind of the best reference image that we could get in this setting. And here are the results corresponding to, again, this is clinical data from a female patient. The left breast is on the top, the bottom row shows the right breast. There are some inserts here that are shown on the right. The first column is showing the reference images, the FISTA TV images within these two ROIs or VOIs. The learned FBP method is in the middle. Again, the learned FBP method is very similar to the FISTA TV. At least qualitatively, they look remarkably similar. The standard FBP method naively applied to the half scan data did not do well as expected, and there's clear artifacts. But again, this is exciting because again, the learned FBP method was trained purely on synthetic data, right? And then just it automatically generalized to the experimental data. Right? This is the type of behavior that we dream of, right, when we're trying to deploy deep learning in clinical applications. And of course, the main motivation that I already alluded to was reconstruction times, right? So the FISTA TV method took 8 hours to reconstruct that image. Again, this is a large-scale problem. The learned FBP method was only about 30 seconds, and 28 of those 30 seconds were used to compute the back projection operator after the filtering was done. So, overall, I would definitely call it a success, so a win case for us, and people in our field are excited about this too. Okay, so I think I can quickly go over maybe a few more things regarding the use of learning to compensate for transducer responses. And I just have a few slides here, but I'll just highlight it. This is kind of review what I already told you about the measurement process in PACT. Again, we start off with our object. It irradiates ultrasound waves. We measure them by a transducer. We reconstruct the data and get an image. Okay? The thing I didn't tell you before was that in practice, experimentalists like to use transducers that have kind of large sizes, right? Because if you make the size, the active area of the transducer larger, the sensitivity goes up. It's just like if you're doing X-ray imaging, you use larger detector pixels, you get more photons, you love it, right? But the price to pay, just like in that application, is you lose spatial resolution. You can compensate for that finite size effect in a model-based method, but again, they're terribly slow. So in this work, we investigated the use of a generalizable deep learning method for achieving that. Okay, so I just told you that neglecting the finite size of the transducer results in blurring artifacts. We're going to propose essentially it's just a data restoration method where we start off with data acquired by a finite size detector. We use a learned model to correct the data, and then we have an approximation of point-like measurements, and then we'll use just a standard reconstruction method to quickly reconstruct the image. Okay. Again, this is just another schematic, kind of just summarizing what I already said. One of the key things here that I'm going to tell you in one moment is how we produce synthetic data for training, and this enabled the model to generalize in a fantastic way. Okay. So the way we generated synthetic data was by using a stochastic spheres model, where essentially we were able to generate spheres of varying radii, varying number, and varying location. And create large ensembles of those objects that are comprised of those spheres. Okay? The good thing about using spheres is that we can analytically compute the pressure wave field generated from them. And if we know the SIR kernel of our transducer, then we can relatively easily compute the synthetic data that would be measured by that finite size transducer. So in this case, we synthesize the pressure signals that were generated by these three spheres, degraded by the transducer size, and then we simply add them up. Okay. So in terms of the networks that we use to actually do the deblurring, we did employ just a standard UNet to basically map degraded data to cleaned up data. But then we also used a slightly more physics-informed approach called a deconvnet. And this integrates more physical knowledge. The basic idea behind the deconvnet is shown on the right-hand side. You start off with your input data, which is your degraded data. It goes into the network. The network basically filters the data using K kernels from a filter bank, and then you also learn how to weight those results to form a final output by linearly superimposing them. So this is a very physics informed. So let me go ahead and just end by showing you some results that this works. Again, we're considering a 3D PACT system here with the hemisphere bowl. In the synthetic results I'm going to show you, we considered a transducer size of 1.2 millimeter by 6 millimeter, which is kind of large. In the experimental results, I'm going to show you the actual physical transducer size was 1.2 millimeters squared. Right? So in order to emulate the size of the finite transducer with the experimental data, we just binned. We basically took five neighboring transducers and binned them. Okay, so first, these are from the virtual imaging results, the computer simulated results. On the left, this is what happens if you just reconstruct using a conventional algorithm and you ignore the finite size of the transducer. Clearly, there's some very strong blurring artifacts. The reference is on the far right. And the middle two are results when you basically reconstruct using a standard algorithm after compensating for the SIR using the learning method. And they both perform well. I think the deconvnet performs a little bit more robustly, but clearly there's a big improvement. And excitingly, these are results from experimental, again, breast data from TomoWave. On the left, this is what happens if you don't compensate for the SIR. The middle two are showing the results where we did compensate, and the reference is on the right, which is the unbinned data, right? So again, this is showing using binned experimental data that this model, although it was only trained using that synthetic sphere data, generalized very well. It could be immediately applied to real-world 3D PACT data, and it seems to have a dramatic effect at improving resolution and degrading artifacts. So I think I'm out of time, so I will end here. Well, hopefully I got to introduce some of you to PACT and convince you this is a kind of a fun modality to work on. It's actually getting quite exciting in terms of the translational potential of the technique. I've shown today that there are a couple problems in this field that lend itself very well to the use of deep learning, right? Namely approximating well-known existing inverse mappings that we don't have access to, but we know exist. So this is really a perfect fit. I also showed you that, again, if you construct a physics-based, physics-inspired compensation method, that we can do a good job of deconvolving instrument response, which is also very, very important. And again, just to emphasize, all the methods I showed today demonstrated excellent generalization performance. Even if we trained on synthetic data, they could be immediately applied to the experimental data. So with that, I'd just like to thank my team who contributed to the results. Sung-Young Park, Humberto Villa, Kevin Huang, Erithik Mert Kam, Pan Chen, Kai Yang, Gangwang Zhang also contributed to some of this. And thank you for the invitation.
Thank you, Mark, for a nice talk. And indeed, I really like the part where you postulate that it exists and you try to use the deep learning to do. And the question I had was about so there is still a postulation that the inversion will be a form of filtering plus the inverse ride-on transform, right? How correct is that postulation? Or can we do better?
Yeah, I mean, it's a good question. So I'm not sure we have to postulate that. We have to postulate that the inverse mapping is linear, right? I guess your question is, if you have a linear inverse mapping, can that always be approximated by the adjoint acting on some filtered data?
Yes.
And it's a good question. I'm not sure. In this case, it seemed to be true, right? Because in the computer simulation studies, when we do inverse crimes and so forth, the profiles were very accurate. So I don't think there's much room for improvement here. But yeah, that is a postulation there. But I think for this class of problems, it turns out to be a reasonable one.
Thank you.
Yeah.
So quick online question from Matt's person. If you are learning a well-posed inverse mapping, does the choice of training data matter at all? Or does the training converge to the same result regardless of your training data?
The training data still matter, right? But they don't matter as much. You still need to have some diversity in your training data. But what doesn't matter is that you don't need to use the exact data that you're going to be testing on, right? You just need to use enough data so that you can learn that unknown filtering operation in a complete, robust way. Which is fine, which means you can generate whatever data you want, right? You can generate your kitchen sink data, just generate random things, throw it into your training set, and that's more or less what we've seen working.
Hi, Mark. Super cool. I like the speed up from using the learned filtered method. I wanted what the filter looked like, if there was some meaning that you could extract from the shape of the filter itself. And a little bit of a follow-up, there were slight differences between the TV Recon and the filter version. And if you looked at a difference image between those, is there structure there that was helpful?
Yeah. Let's see, where is it for the, for here. Yeah. So wait, could the first part of your question, could you repeat that?
The filter itself.
Oh, the filter, yes, yeah, good, sorry. I was busy moving the slides back. We wanted to look at that. We looked at it, but there wasn't something obvious that popped out. You would hope that, by analyzing the shape of the filter, it would inspire a mathematician to derive an analytic closed form of that. But we haven't quite gotten to that far yet, so I'm not sure how much inspiration it's going to provide for mathematicians. In terms of the TV result, yeah, there are slight differences. That's true. But you kind of expect that, right? I mean, the Vista TV is not a perfect reference. In this case, you have to tune a regularization parameter and things like that. So the only claim I want to make here is that the learned FBP method resulted in images that look similar to the Vista TV method, and they're much more accurate relative to that method than is the standard FBP method.
Thank you.
Thank you again, Mark. Great job.
All right, thanks.